Hello, welcome to the problem session. Today we have a problem in using accelerating frame. So, like accelerating frame. So, there's a background to this that you may want to kind of refresh on. It's like when you have F equals ma for unchanging mass system, this is an inertial frame. But even if the frame is accelerating, like suppose you want to study this by something which is a frame that is attached, which is moving with the car. If you want to study in that, then you will have a fictitious force. So this thing will change to mass acceleration. In addition to this acceleration, you'll have this also acceleration plus acceleration, and so your force will look like this: acceleration of frame plus acceleration and mass of your body. Sometimes we say that F minus ma equals the acceleration of the mass itself, and this thing we call it fictitious force, because there's no force. It's just because of frame I'm using, which is not inertial frame, right? So you write F plus F fictitious equals ma, and F fictitious is m minus ma. Okay, now that we're going to use we'll use accelerating frame to solve this problem. So let's look at what A is saying. A is saying is there is an angle theta at which this remains in the same direction. This doesn't kind of rotate around. It doesn't wobble or anything. It just remains steady. So let's look at rotation of this. So at the center you'll have a force of gravity at L/2, and then you have a fictitious force ma, which will be in that direction, minus ma, which is F, say F fictitious. Now if this is the pivot point, and so rotation, and there are forces over here at the pivot point. We don't need to know the forces. If I want to know the torque about point O, so net torque about O will be 0, right? So using these two forces, you can see that mg has a torque L/2, and from here to here, this is the lever arm, and this is L/2 on this side. So this is cosine theta, and this has a clockwise, that's a minus, and the other one is a counterclockwise, so it's going to be plus minus a. This force is this minus is this is just a magnitude ma, and that's going to be L/2 sine theta equal to 0. This minus here is because of the vector, gives you opposite direction and not included in the magnitude, right? Okay, so you can see that this can be, a lot of things cancel out, and you have a tangent theta equals G over L. So this is a condition on theta to be equilibrium. So theta will be basically at equilibrium, arc tangent G over L. Okay, for B, we are going to displace it a little bit about that. And again, the forces are the same two forces. So if I'm over here, we have this L over 2 distance, and this mg, and you again have ma in that direction, because A is in that direction for the frame. Okay, this time it's not going to be equilibrium, so I'm going to have moment of inertia about this O, I about O, and then d square phi dt square equals minus mg L over 2 cosine theta plus phi minus plus m a L over 2 sine theta plus phi, and phi is small. So we have a small angle, and we have a relationship over here for theta. So let's expand this, and so you expand this mg L over 2 cosine theta cosine phi, and this is a plus angle, so we get a minus, kills the minus, becomes a plus mg L over 2 sine theta sine phi. That's from here, and from here I'm going to get plus ma L over 2 sine theta cosine phi, and plus mg ma L over 2 cosine theta sine phi. Okay, so let's see, this can be replaced by 1, this can be replaced by phi, this again replaced by 1, this can be replaced by phi, and when you do the replacement, you can see that from here this cosine theta and this sine theta, these two terms will cancel. This is 0 by using equation 1 by 1. So that's about equilibrium condition. And over here you have a, yep, so and this one is because on the edge the moment of inertia will be 1/3 ml square. So we have d square phi dt square, that should be a, this minus with this plus, there should be a minus sign. We have messed up a minus sign somewhere, so I'm going to put a minus sign here. Minus, you should figure out I messed up a minus sign here. And this should be m L over 2 g sine theta plus a cosine theta, and on the other side divide by 1/3 ml square. So one of the L goes away, M goes away. So I have a -3/2. Maybe you can see that you got a G sine theta plus A cosine theta, and from here we have a tangent theta is G/L. So if you think of this as P/B, then you can actually write down sine theta is G/square root of this is A, G square plus A square, and cosine theta will be A/square root of G square plus A square. So over here is going to be A square over square root of G square plus A square, and this will become G square over square root of G square plus A square. Oh, there's an L missing from here, L here, okay? And then you can simplify that, and that's -3 and times phi, this phi over here, 3/2L is square root of G square plus A square, this whole thing times phi. And so this equation is a simple harmonic oscillator equation, and so it means this will go back and forth, swing back and forth about the equilibrium direction, and with frequency, angular frequency will be a square of that will be this quantity, 3/2L square root of G square plus A square. So another way to write down is time period will be 2 pi over omega. So you can see square root, take a square root. So 2 pi over square root of this stuff, 3/2L square root of G square plus A square. Okay, that's a pretty interesting problem. Just to recap, this problem actually hinges on your understanding of how to use this is when a frame is accelerating. So in an accelerating frame. And this is very useful actually when a frame is accelerating. So you can think of this as a fictitious force. You bring ma on the other side and then use a regular technique. You can actually think of fictitious force like a real force. There's nothing fictitious about it. You actually feel the inertial effect of it. So this is a very important. Okay, that's it. So we'll do another problem in the next session. I will see you then. Bye.